Hi friends, my name is Narsimha and I'm studying my BTech in IRE College. Today, as a part of my AIT Tech Talk videos, in the subject of database management systems, I want to explain about a topic named high performance with an in GPU, which is shortly abbreviated as graph database caching. In our daily life, in our day-to-day life, everything, the records of ours of a person is in database. So today I want to explain about a topic named high performance with an in GPU graph database caching. First of all, what are the graph databases? A graph databases are specialized to store and manage graph structures consisting of vertices, edges, and their properties. Graph databases are the structure of vertices, edges, and their properties. Graph databases could represent complex network structures, but they currently underperform for this task. To improve performances for graph databases queries, the authors propose caching the graph databases in distributed graphics processing units connected with a 10 gigabit Ethernet network. In this slide, I want to explain about the definition of a graph database and the cons and disadvantages of graph database is that are underperformance. The high performance is not observed in this task of representing the complex network structures. The representation of simple network structures are achieved by this graph databases, but the complex network structures are underperformed for this task. So, although conventional relational databases are useful in representing one-to-one and one-to-many relationships, representing many-to-many relationships as graphs is not trivial. Graph databases can represent complex many-to-many relationships simply by adding the edges. Means the nodes are the vertices. By adding two vertices as an edge, we can represent the complex many-to-many relationships. A small example, a graph database is shown below. Here we can see one vertex of customer, one vertex of order, and three vertices, three nodes of product. Here customers place order, and from order, it includes the product. Just have a look about that small graph database example by which you can get an idea of it. Next, more graph performances with more GPUs. GPUs means which have specific graph database caching. By using more graph database cache, we can increase more graph performances. GPU processing is a widely accepted solution for boosting graph algorithms such as SSP and breadth first search. A distributed graph processing system is illustrated in other work, as is one using GPUs. The massively parallel architecture of GPUs can be fully exploited if a graph structure can be stored inside the GPU device memory. Otherwise, frequent transfer of a graph structure between the host and GPU device memory overwhelm the performance benefits. Next, this is a small pictorial representation of distributed in GPU graph database caching. Here we can see in the first diagram the server, graph database, and graph caching in memory, property ready query, and response. Here which is inside, and the outside is graph drivers, search query, and response. In the next one, we can see the kernel and results. In the two boxes, we can see the graph caching and the original graph. Just have a look. And that's connectivity of two boxes. In the last one, original graph, the connectivity of the two vertices or the nodes by the edges will give and clearly representing the graph databases. Next, the graph cache is partitioned and transferred to the distributed GPUs for GPU-based high-performance graph processing. The graph database and the graph cache are working on the same machine and connected to the distributed GPUs via the 10 GPU network. Two types of data are extracted from the graph database and cached in the proposed graph cache. The two types are, first one, the graph structure, which consists of vertices and edges. and is required for graph traverse and search queries. And the second one is the selected properties of vertices and edges that are frequently requested for property read queries. Next, the types of queries are processed as follows. First one, there are three types of queries: property read query, graph traverse, and search queries. Well, coming to the topic, property ready query. If the requested properties are cached in the graph cache, the graph database returns the result from the graph cache. Otherwise, the graph database processes the query as usual. Means this is specifying that. So in the property ready query is saying that if the graph database returns the result from the graph cache, otherwise the graph database processes the query as usual. Means the changes should be done to the query. Next, second one, graph traverse and search queries. The graph database invokes GPU kernels on the appropriate GPUs over the 10 GBA network. It then collects compute results from the GPUs and build a final result. Next, listen to the next slide. Graph cache structure. Each component, such as a vertex or an edge, which is also known as entity, is implemented as a Java class to fully enjoy the benefits of object-oriented programming. The OOPS concept is well known to us, that is object-oriented programming concept, which is well known in Java. So that is the reason each component, such as vertex or edge, is implemented as a Java class to enjoy the benefits. Such object-oriented design is well suited to database purposes, but there is still room to reduce the memory footprint and improve the graph traverse and search query performance. Query processing with a graph cache. The graph cache can process the three types of queries. This subsection introduces processing methods suitable for each query type by graph cache. First one, property ready query. If the requested property is cached in the graph cache, the corresponding vertex or edge ID is extracted from the query. The memory address of the requested property value is computed based on the vertex or edge ID and property name. Then the property value is read from the address. Second one, traverse query. Given that distributed GPUs over a 10 GBE network are used for traverse queries, the graph cache is partitioned and then assigned to these GPUs. In principle, CSR arrays in the graph cache are partitioned so that each partition is fit to the device memory of a single GPU. Because a graph is cached over multiple GPUs, a traverse query also spans multiple GPUs, resulting in frequent synchronizations among them. The synchronizations for each traversal on boundary edges outweigh the benefits of distributed GPUs. Next, graph search query, the third query. Unlike the traverse query, the graph search query always involves all the distributed GPUs. Whereas based on the traverse query, this graph search query is somewhat different because it involves all the distributed GPUs. The compute cost for a graph search query is typically much higher than that of the for a traverse query. And the barrier synchronization overhead can be justified without batch processing. Thus, graph search queries are performed sequentially using all the distributed GPUs. The synchronizations are implemented via a DSP, as with the aforementioned traverse queries. Graph search query. In this experiment, SSSP is used as a graph search query. This figure shows the SSSP execution times of ERIC 1 cache and 1 cache 1 GPU cases on the random graph and 3 real graphs. I couldn't show the picture. So although the compute costs of the property read and traverse queries do not change depending on the graph size, those of the graph search query increase as the graph size enlarges. Thus, the execution times increases as the number of vertices increases in all cases. In all the cases, in the last lines are specifying that when there is an increase in the vertices or the edges, or the nodes, the execution time will be increases. Finally, to the conclusion. Graph databases, especially for Travers and graph search queries, currently underperform. To compensate for these weaknesses, we proposed an in-GPU distributed graph cache in which vertices and edges as well as selected properties are extracted from the graph database as a simple array-based cache that is then partitioned and cached in network GPUs connected with PCI Express over 10 GPU. The cache size can be extended by adding more GPUs to the 10 GB switch. In this session, I want to explain that the graph databases are well known to represent the simple structured data. But while coming to the complex structure, the underperform is observed. So to overcome the underperform, the concept of in GPU distributed graph cache is introduced by which the performance can be increased. The high performance can be offered by the graph databases. So thank you, friends. I hope my lecture is useful for you and it will be useful to understand about the graph database and the high performances by using the in GPU processing in the graph databases. Thank you.